Hello, my name is Rob Reynolds. Welcome to Calc 1. Today's lesson is on section 6.2. We're going to be looking at regions between the curves, or finding the area between the curves. And basically, I'm going to be talking to you about taking the upper function and subtracting off the lower function. For example, if I integrate the upper function, I'll get this area. And notice I'll come all the way down to the axis here. In blue, but then if I integrate this area in red, I'll also get this little piece here. So what's happening here is if I take the blue, which is positive, and subtract off negative area, that's like adding this area, which is exactly what I wanted to do, to find this area between. And then over here, I'm taking the blue, and then I'm subtracting off the red. So it's really positive minus positive area. And that will just cancel out to be zero area, which I don't want to count any of that area. So basically, it's the upper minus the lower function. Sometimes the hard part, though, is actually trying to find what we should integrate from and to. So this problem gives me a little bit of a hint and says that it's bounded by the y-axis. So I am going to go from 0 to some number. And I don't really know what that number would be until I find the point of intersection. So I could do a little bit of math, and this is a difficult problem to find the point of intersection. But basically, if I just set the two functions equal to each other, I should have points of intersection. So finding a common denominator and then cross multiplying, I'll have 2 is equal to 2x minus 1. I'm foiling out this side. So all of this is this. Setting equal to 0 and reorganizing some things, hoping that I could factor by grouping. But I don't really see a common factor. So I'll try some synthetic division. And I know that 1 is a factor if I try the rational root theorem, p divided by q. So I'm just going to try positive 1, and if that doesn't work, I'll go to negative 1. So bringing down the first term is a 2. Adding is 1, multiplying, and adding, and multiplying, and adding. And sure enough, I did get a point of intersection. And so now I know I'm going to integrate between 0 and 1. Probably a little bit easier method would be just pull out your calculator and find the point of intersection. So I'll ask it to graph it and go ahead and just calculate the point of intersection. I don't even really care what this looks like. I know I'm going between 0 and something, so to find that something, now I can see that it's 1, and the height is only 0.5. So you can zoom in here and actually see the graph just a little bit better. And you can see that I'm really interested in that point right here at 1, 0. Of course, while I'm here, I might as well go ahead and just find the area for checking purposes. My lower bound now is 0. My upper bound is 1. And it'll fill in between 0 and 1. But notice it's only doing the top function. So I'd actually have to plug this in a little bit differently. Because this is not the area that I'm trying to find. So if I go back to my calculator and actually put in the upper function minus the lower function and ask it to integrate between 0 and 1, I'll get a decimal equivalence, which is 0.785398816. But I'm not interested in that decimal answer. I'd really like the exact answer. But at least we can record this and try to make sure that we actually get an equivalent answer to this So I recorded this decimal to make sure that I will end up with this as an answer, but the calculus part would look like this. So I'm just taking the upper minus the lower, and I'm going to integrate. Get rid of this graph because we've already looked at the graph. So I need just a little bit of space here. So this is this. And the integral of 1 over 1 plus x squared, if you remember, is tangent inverse. This is going to be x squared divided by 2, and this will be plus 1/2 x. And then I want to evaluate that between 1 and 0, and record values for f at 1 minus f at 0 doing the fundamental theorem of calculus. So this is the tangent inverse of 1, which is pi over 4, because the tangent of pi over 4 is 1. And this is going to be minus 1/2 plus 1/2. And of course that will, well, that's all f of 1. But when I go to plug in the 0, I'll actually get a 0. So I'm actually just subtracting off 0. And the final solution then is pi over 4. And I'll go back to my calculator and make sure that pi over 4 really is that decimal that I needed. Here's how the author worked it out, but they had the same solution. And there's just a little bit enlarged graph. So this next picture, again, is unknown to me. It's a line and an absolute value function. So I know it looks something like this and has a y-intercept of 3. But again, I'm not real certain of those points of intersection. So to find those points of intersections, I'll set the two functions equal to each other again. And if you remember, for absolute value, it's either that value or it's the opposite of that value. And I could put the negative on either side here. But over here, I'll get x equals 3, and over here I'll have 3 equals negative 3x, or x equals negative 1. So that's really helpful because now I have integration points from negative 1 to 3, and I can see that that's where I want to integrate from. But I still have a little bit of a conflict because the function above here and below here is different than the function above here and what's below here. So I can't just say green minus maroon. Actually, what I'm going to do is then I'm going to integrate from negative 1 to 0, because I have a point of intersection here at 0. And so then I'll do the green minus the maroon. So the green function is the line, the upper function, minus the lower function. And the equation of the lower function is just a line. In fact, I wrote it down here. It's negative 2x. So absolute values are just two lines. So it's minus a negative 2x. But then I'm going to add the integration from 0 to 3 of the upper function, which is still the green line, minus the lower function, which is, well, that's the absolute value. It's the positive side of the absolute value. So the hard part's over. the easy part then hopefully would be the number crunching. So combining like terms, integrating, and evaluating. F of, if I throw in a 0, I'll get 0. This is going to be 3 halves minus 3. And this is negative 9 halves plus 9. And then minus the 0. So I would say that this is the step that your professor is really going to be looking for, that you probably don't want to omit. So don't do too much number crunching here in your head or on the calculator, because you're trying to prove to your professor that you understand this f of 0 minus f of negative 1 concept. And again, we integrated with respect to x, and that's why we were filling up boxes going this way, from left to right. So that's with respect to x. And again, this is probably the important step here. Well, we don't always have to integrate with respect to x. Sometimes we can look at the change in y, and then I'm not talking upper function minus the lower function, then I'm talking the right function minus the left function. So it's kind of just taking my image and just thinking about rotating it. So now it's upper minus the lower, and then my x became my y and my y's became my x's, where here it's right minus left. So the reason that we might want to integrate with respect to y is because my upper function minus my lower function over here is different from my upper function and my lower function over here. So I can't really do upper function minus lower function this direction. But if I do the right function minus the left function, that stays consistent. The right function is always the red, and the left function is always the black line. But in order to do that, I'll need to solve each of these equations for x. So taking the cube root of both sides, I'll have x equals the cube root of y. And over here, easy enough, x is equal to y minus 6. So now I'm going to find the point of intersection. Again, either I can use a calculator, or I could quickly just set the two functions equal to each other. So the first y was x cubed, the second y is x plus 6, and again, this is not going to be factorable. So I would try some synthetic division again, and I might try 1, remembering to throw a 0, a placeholder in, for x squared terms, but this doesn't turn out to be a 0. So then I've got to try other factors of 6. I could try negative 1. Eventually I will try a 2, because that's a factor of 6. So bring down the first term, multiply, add, and I finally found it. So the x coordinate here is 2, and that's important because that's going to tell me what I need to integrate from. But that's with respect to x. If I'm integrating with respect to y, I'm actually filling up rectangles this direction. And so I'm going to start here at 0 and fill this all the way up to the y value of 8. So this 2 can be plugged in anywhere. I'll plug it in here. So 2 plus 6 is the y value of 8. So I'm going to fill up starting at the bottom, I'm going to integrate from 0 to 8, and I'm going to do the right function minus the left function, and now I'm in terms of dy. So integrating this and evaluating between 0 and 8 gives me, again, this is probably the step that your professor would be looking for. There's your f of 8, here's your f of 0, and then the solution would be 28. Here's how the author decided to tackle this. So the last example says find the area, and we could actually do this a couple different methods. The first method we could use calculus, and then the second method we're just going to look at, see if we can just use some simple geometry to find the area as well. So the first method, I'm going to, let's graph the function, and then the direction said I'm only interested in the first quadrant. So I'm going to calculate the point of intersection on my calculator by identifying the blue curve, the red curve, and then my guess is over here around 5, 6, 7, looks like it's 8. So if I just integrate, though, from 0 to 8, I won't get the area between the curve. In the first quadrant, remember, I'm looking for, so if I integrate this way, I would have to find this point of intersection, I suppose, because this would be the upper minus the lower. In other words, going vertically, I would have to do 2 problems. I think it would be faster for you to think about doing what we had done on the previous problem. The right minus the left looks to be consistent. So I'm going to do the red function minus the blue function, but then I'm going to integrate dy, which means bottom to this top point, which I believe is 4. So I'm going to integrate between 0 and 4, and the top function is the line, and I'll subtract off the bottom function. So integrating gives me 1/2 y squared plus 4y minus 2/5 y to the 5 halves, excuse me, from 0 to 4. I'll let you try to fill in this area, which is really the most important area, and see if you don't get the 56/5. I'll leave the number crunching to you. But there is a second method, this geometry method, that we could try to approach. If we were to explore that dx method again, and looking at these rectangles, this area is going to fill up here in blue, and it would continue to fill up all of this area. So if I were to integrate from 0 to 8 of this x to the 2/3, I would find all of this blue function. And then to use geometry, I notice I have just a nice rectangle here. So I can just subtract out the area of the, excuse me, did I say rectangle? Triangle. So I have a nice triangle in here. And it looks like the base here is 4 and the height is 4. So I know that the triangle is just 1/2 base times height. And integrating this gives me the same thing as we had before. and I'm going to integrate that from 0 to 8. So again, I have 96/5 minus this area of the triangle, which gives me the same answer as I had before. So it's possible to integrate this in terms of dy, which I think I like better. It seems a little bit smoother, right minus the left, but it's also possible to do a little geometry trick, and you can do it with respect to dx, but then just remember to subtract out this triangle. This is a little bit better picture for the author's drawing and the author's explanation. So we did it two different methods, right minus the left, and we integrated everything between 0 and 8 and then subtracted off that triangle. If you have any questions, feel free to email me. Hope this was helpful.